So I'm hoping that there are people here from multiple disciplines, and I want to really encourage you to come to the other lectures that we have. We have one more this semester, so I want to tell you quickly about it. Charlaos Papadopoulos will be speaking from the Computer Science Department next Thursday in this room, next Thursday at 3 o'clock in this room. His talk is called Looking at Bits and Bytes, the History of Virtual Reality. Okay. So without further ado, I want to introduce the advisor for our student today. Professor Artem Organov is going to come up and introduce him. Thank you very much.
It's a great pleasure to introduce Qiang Zhu, a PhD student who recently finished his PhD in my laboratory after 3.5 years of research. I think we are all very happy and proud of his accomplishments. He not only finished his PhD much shorter than a normal PhD student. During that time, he published about a dozen papers, including Nature Chemistry, Physical Review Letters, and so on and so forth, and has written 4 important pieces of computer code, big computer programs, each in itself. And Qiang has become so successful that actually over this weekend I received 3 letters from my colleagues in China, from top institutions, each informing me that they are going to offer him a professorship. I think we should do something about that. And for now, let us welcome Qiang and his talk on one of the most challenging and dynamically evolving fields of modern science, crystal structure prediction. Field which was barren for a long time, problem which was believed to be intractable for a long time, and which was the stumbling block on the way to computational material discovery. Now this problem is solved, and significant credit for that has to be given to him. So let us welcome.
Thanks for the introduction and good afternoon. I'd like to start this lecture by introducing 2 crystal structures of carbon nanotubes. So graphite and diamond, both of them are well known to everyone, and they are viewed as the most fundamental crystal structures in crystallography. However, to predict them has been viewed as a mission impossible for a long time. Dating back to 1988, there was a famous paper by Geosciences. He summarized the situation of crystal structure prediction as a continuous scandals in the physical science. And he said that it remains in general impossible to predict the structures of even the simplest crystalline solids from a knowledge of chemical composition. For example, who would guess that graphite or diamond is the thermodynamically stable allotropes of carbon at ordinary pressure conditions? So, used to be a mission impossible. However, today, after another 25 years, I'm standing here and I'm very delighted to present another different picture of crystal structure prediction. Now we can use it as a ordinary tools. And here I would like to introduce my work during my PhD, crystal structure prediction and its application in earth and material sciences. So this talk would be organized in such a way. Firstly, I would like to introduce the basic introduction of crystal structure prediction, and then I will move on to illustrate these functions by applications into 3 different fields. Firstly, I'd like to introduce to you to discover variable stoichiometry of materials under extreme conditions. And secondly, I would like to show another function to predict crystal structures from molecular building blocks, which allows us to predict molecular crystals and molecular compounds. The last session is to optimize properties, which allows us to search for materials with target properties, which would be a fascinating tool for material science. So first of all, crystal structure. So what is crystal structure? Suppose most of the materials under thermodynamical equilibrium, they will form some state which has long-range order and long-range symmetry. We call it crystal structure. The crystal structure is the basis for understanding materials as it determines their properties and behaviors a lot. So in last century, a big branch of modern science is to discover how to solve the crystal structure and how to understand crystal structures. Due to the pioneering works by those Nobel figures, today we already know how to solve the crystal structure. Just we take a sample, a piece of material, and we go to the laboratory and just do a pretty ordinary experiment, X-ray diffraction pattern. And from the pattern, we can exactly understand the crystal structure. However, if we want to do crystal structure search from another point of view, computer modeling, then it requires a concept of crystal structure prediction. But can we predict crystal structures? As I mentioned, it used to be an impossible mission. And people try to do this in such a way. So firstly, they pick all the possible candidate structures from database, from experiment, and from other channels. And then they select these structures and do energy evaluation at different levels, at the classical level and the quantum chemistry levels. And then among them, they pick the structures with the lowest energy as the ultimate solution. However, we can immediately see that this approach is generally not reliable, as it's very likely that we miss the key structures. And if the structures is not on the candidate list, we eliminate it, and then we cannot approach to the right answer forever. So we can say that this method can be viewed as a tedious additional approach that it's very likely to fail. So this motivates us to proceed to the modern crystal structure prediction. So by modern crystal structure prediction, it must satisfy the following criteria. First of all, it must be reliable. By reliable, it means that for each individual structure energy evaluation, it must be accurate. And for the global search, it must be trustable as well. So the method has to be universal. If this method can be used to predict a structure for a particular system, then it must equally work well for other systems. And from the computational point of view, it must be economical. It means that we do this by supercomputers, so we must make sure that this calculation can be done in a feasible time scale. And if we want to make it as a software, then to let people with limited background to use it, so we must create a good user interface so that the program can perform the search automatically, while people just need to give some very basic input information. So following these criteria, we designed a so-called Woodpecker method, which is a universal structure predictor of evolutionary extography. This is a method based on evolutionary algorithm. It mimics the biological evolution, and it starts from the basic chemical formula, and contains a very powerful searching process, so that the searching is invariant with the system, and it can learn from the process itself. So here I will just give you a very brief introduction of this method, and if you want to dig more details, I recommend you this excellent review paper here. So how Woodpecker works? So remember that it starts from the very limited message, as user just needed to specify a chemical formula, and then the program it generates structures based on this chemical formula, and then the structures are relaxed by other quantum chemistry code like WASP. The structures are guided by energy and then selected to generate the new populations. And when we do selection process, the program always favors the low energy structures. And the standard evaluation operators are as follows. Firstly, we can choose two parallel structures and then combine them together and get the new structure. Or we can just take one parallel structure, mutate the atoms or the lattices, or swap the atomic positions for different chemical identities. So and then after this new population generation process, we go to the new population and then population by population, because the evolution nature of this algorithm, it can gradually improve the searching process, find the structure with lower energy until it reaches the ground state. So the principle of this method is very simple. However, when we apply this method to different systems, we need to find many fascinating results. For instance, like for elemental form of boron, it can behave like a ionic compound of sodium chloride at high pressure, while another case is sodium, which is viewed as a good metal at normal condition, becomes a transparent insulator. So we began to release our code in 3 years ago, and just within 3 years, we already received 1,300 people who tried from different institutes and universities who tried to apply our method to different systems and to conduct their own research. And we already have over 100 papers have been published based on applying this method. So here in this lecture, I will focus on the projects which is related to my PhD research. So the first one is variable stoichiometry studies of materials under high pressure. By studying this, I'd like to introduce you a well-known puzzle in geochemistry. So the so-called missing zero paradox. Dated back to 1977, there was a famous paper which pointed out that our atmosphere contains far less xenon compared to other lighter, lower gases. So where are the missing xenon and what's the reservoir of missing xenon? For a long time, geochemists speculate that the missing xenon would go into the deep earth of mantle. And they proposed a hypothesis that xenon might be stored in the earth's mantle in the form of compounds with perovskite, oxides, or silicates, and so on. Most likely, they viewed that oxides could be the most possible candidates. So the question is, would xenon form as the inner elements, well known for everyone, could form some compounds? So we should let's study the xenon chemistry first. At ambient condition, many chemists already tried to synthesize these xenon-based compounds, like xenon fluorides, xenon oxides, and so on. And the conclusion is that they indeed find xenon can exist multiple valence states to form some compounds with molecular compounds with fluorine or oxygen and so on. But the problem is that this molecular species can form extended crystalline states at a higher pressure, the pressure of Earth's mantle. So to confirm this, we can do either experiment or theoretical calculations. However, experiment is requires very high cost. So here, theoretical calculation will play a major role. So we applied our method to predict the zero oxide system at a wide range of pressures and some given chemical stoichiometries. As we know, we already found that xenon can form like +2, +4, +6, and +8 valence state. So we studied the possible compounds of XeO, XeO2, XeO3, and XeO4. Before we analyze our results, I'd like to just give a very brief introduction about how to evaluate the stabilities for the compounds with different chemical compositions. Suppose we have two elements, A and B, and if it forms compounds AB, if the formation energy of AB is negative, then we say AB compounds AB is stable. Otherwise, it's unstable. We can transform this reaction into the left panel of the graph, so that if we have a structure which has energy above the composition, above the so-called AB decomposition line, then we say this structure is unstable. If the energy is below the line, and then it's stable. If we have another composition, say AB4, and from this picture it seems that this structure should be stable because it's below the decomposition line, as I mentioned. However, it will decompose into AB plus B, so it's still unstable. So the recipe for this, the criterion for the stability of desired structures is that the energy must be below all the possible decomposition lines. So that's how we analyze this. These figures, these data. So the stable structures will get together from a convex Hall geometry. So with this concept in mind, we can go ahead to analyze our results. Remember, we have studied 4 different chemical compositions from XeO to XeO4. When we analyze our results under relatively low pressures, like 50 GPa, then we found that all of these energies are above the composition line of elemental xenon and elemental oxygen. It indicates that these compounds would be unstable. However, if we apply pressure about around 100 GPa, which is exactly the pressure scale of earth mantle, we found that XeO and XeO2 become stable. And then if we increase the pressure further, and then we can clearly find the trend that the stability of the compounds can be significantly enhanced by the pressure. So with this, we can get a full picture about this system, the stable compositions, and the corresponding stable crystal structures. So some people might argue that if we just all of these calculations are done at 0 Kelvin. So, but imagine that in the Earth's mantle condition, it must be on the very high temperatures. So we should include the effects of temperature. So we did this by a so-called quasi-canonical approximation method, and then we studied the effects introduced by the temperature, and we found that when we increase the temperature, the shape of the convex hull doesn't change at all. So it means that the thermal effects does not qualitatively change the stability of this structure of those zero oxide structures. So in this, we can propose the stability of zero oxides at high pressure And this example also shows us an important rule in that new stoichiometry compounds might exist under high pressures. So the problem is that how can we predict the stoichiometry? So for the zero oxides, we learned the hint from the ambient pressure behavior. We know that zero might form like +2, +5, +2, +4 to +8 while state, so that we can figure out the possible chemical composition for zero oxides. But if we doesn't know this information, can we predict them automatically? The answer is yes, no. So we designed a method which can just use one single time calculation. It can yield out all the stable chemical compounds for a given system. So it works in such a way. Firstly, we generate structures from a random chemical compositions, and then we analyze these energy scatter plots, and then we can get such a Thomas Hall. And then we evaluate the fitness function of these structures by the distance from the energy scattered to the nearest Thomas Hall. So that we can move on to the selection process, and then we use these structures as parents to generate new structures, so that we can gradually establish the Thomas Hall and optimize it until we can find the right ground state and the right solution. All the stable chemical compositions and the corresponding crystal structures. So this is a very useful functions. So when we try to apply this to a wide range of systems, the first one is sodium chloride. Sodium chloride is, as we know from the high school chemistry book, it's a well-known crystal structure and well-known material, and no one can expect anything except sodium chloride structure for this system. But if we increase pressure, and we found that this system actually displays a very exotic chemistry. For instance, when we tried like 25 GPa, we found another brand new compound. NaCl3 becomes stable. So in this way, it means that at that condition, these compounds can have equal chance to exist, just as sodium chloride, the one we saw it every day. So when we increase pressure further, we found that actually for this system, it can have many different stoichiometries, from sodium-rich boundary to the chlorine-rich boundary. For instance, for this particular system, 1 to 7. If we don't know any knowledge about this, can we expect such kind of exotic compounds? NaCl7 can exist at pressure, but the calculation shows yes, it is. We also studied another system, magnesium oxide, which is one of the most abundant material in the Earth. So we expect to find something new for this system as well, just like what we did for sodium chloride. And indeed, we find several stable compounds. For instance, at the oxygen-rich condition, we can find compounds called magnesium peroxide, which is well known for chemists. But for the magnesium-rich condition, we can also find a brand new compound which has the formula of Mg3O2. This is quite exotic, and it can be stable from around 500 GPa. Of course, this pressure condition is already exceeds the pressure of the Earth. However, if we go to the whole universe, as we know, the magnesium oxide is a rich planetary forming materials. So it's quite possible that such of compound can exist as some planetary interiors. So the next part is to predict structures from molecular units. Above, I mentioned how to predict the structures from the atoms, particularly for the inorganic crystals. But we all know that organic crystals can be also important, so we want to figure out a way to predict the organic crystals as well. But if we predict these organic systems, we must understand the difference between organic crystals and the inorganic crystals. So they can be different in many aspects. Firstly, usually a molecular crystals contains many atoms, and the molecules has very big interaction. That the unit cell usually contains many empty space. And another important feature is that many organic compounds are actually metastable. By metastable, it means that they are not, by energy, they are not the ground state. So if we take a chemical compound like C2H5NO2, which is actually a type of amino acid, the basic origin of our life, and if we do prediction for this particular chemical system, we found that the ground state is not the structure based on the molecular form of amino acid, but a mixture of small molecules. So it proposed a issue is that we need to avoid such kind of decomposition of the molecules when we perform our search. So the most straightforward way is to apply constraint. So we can treat it as a whole building block. So during any operations, we always keep the geometry of this building block. We constrain it as a rigid body, so that the benefits from this is not only that it can prevent the decomposition, but it can also decrease the number of degree of freedoms for each molecules, and then which can further decrease the searching space quite a lot, which is exponentially related to the number of degree of freedoms. So in this case, we are no longer doing global optimization, but constrained global optimization. Another important feature of molecular crystals is that they have a pretty uneven symmetry preference. So just to compare the symmetry distribution of inorganic and organic crystals, we found that organic crystals usually prefer some particular space group very much. So it indicates that when we perform our search, we don't need to scan all the possible configurational space. Instead, we just need to focus on these particular space groups which are favored by nature. So we invented such an approach to construct the symmetrical structures according to the desired space group. And then we can further construct a new algorithm, constrained evolutionary algorithm, to predict molecular crystal structures. This algorithm is quite similar to the standard evolutionary algorithm. The only difference are we will apply constraints on several key stages like initialization and the local optimization and the variation operators. So remember that when we generate new structures from parents, we have a set of variation operators like periodicity, mutation. So in this case, we use the same approach, but just different technical implementation. We treat the molecules as a building block, and the building block would always have the same geometry during these variation operations. So we applied this method to a wide range of molecular crystals, like small molecules, the water, ammonia, carbon dioxide, we can easily find the ground state just in a short time scale. And we can also work on a bit complex molecular crystals like benzene or glycine. We found that to determine the ground state, it can be quite also like a piece of cake in our method. So this encouraged us to work on some really complex systems, which can be illustrated by the identification of solid methane A phase under pressure. So methane is considered to be a major component in planets like Uranus and Neptune. So to understand the solid phase behavior of methane under pressure of planet's condition is of great interest in planetary science. So however, when we look at the phase diagram of methane, we surprisingly found that this phase diagram is quite complex. And most of the crystal structures are poorly known from the experimental point of view. And the recent interest is focusing on the so-called methane A phase, which can be stable around 5 to 10 GPa. And this structure, according to experimental observations, they found that it has a very complex unit cell which contains 21 molecules in this in each unit cell. So 21 is quite an unusual number in crystallography and also a big number in crystallography. So that's to solve the exact crystal structures, it requires a substantial big amount of efforts for both experiment and theory. So, but we tried our method. Surprisingly, just within one day, we found a very low energy structures, and when we compare these structures with the experimental results, we found they can match very well. And just during the period of our work, another experimental group published the experimental high quality neutron diffraction pattern, and then they proposed a structure based on this pattern, and we found that this structure is exactly what we saw in our evolutionary research. So with this structure model available, we can further analyze this particularly unusual number of 21 in crystallography. We can view it as a hexahedral-based packing. So 21 molecules can be viewed as in such a way. 12 molecules forms the hexahedral, and then another one molecule is sitting in the center of hexahedral, and the rest of 8 molecules are outside of hexahedral, taking this size usually above the face center of hexahedrons, and thus form a high symmetrical structures. And then using this hint, we can potentially analyze many complex crystal structures with unusual number, and our research can provide a good possible solution. So we further improved the variation operators. Remember, during our variation operators, we have an operation so-called rotational mutation. So which is to mutate the molecules and then form a new structure. So we improved this formula. Firstly we can calculate for a given shape of molecules. We can calculate the principal axis, so that when we perform rotation, we can always choose the principal axis to rotate, which is much more efficient than the previous formula. And we can also allow the prediction of flexible molecules. Just in this case, we need to allow the variation of dihedral angles to allow these molecules can have different conformations. So use this improved technique, we we proceed to predict the very complex molecular crystals between 1,4-dialuminum dibromide. And if we tried this before we have this technique, then it takes quite a long time and we didn't find this solution. But with this improved technique, we can trivially find this ground state just within 1 day's calculation. We are also testing some new functions. Recall that I mentioned, so for the elements, if two different elements, they might form compounds. And the stoichiometry of the compounds will vary with the pressure. So we wonder if the same thing can happen on molecular compounds. So the two different molecules, they can also form some so-called molecular compounds, or in another term, we call it co-crystal. And this compound that will the ratio of the compounds vary under the external conditions. This is quite an open question, and we just try, but we can use this function, variable compositional molecular compound search, to perform to search for the answer. And here is just an illustration of simple example, the possible compounds for molecular hydrogen and molecular water. Another ongoing function is to predict polymers. As we know, polymers is usually can be viewed as a very complex system, as it has a huge amount of variables. But we can still implement some functions to predict starting from the monomers, we can predict the possible configuration of polymeric chain. And then further, we can use this polymeric chain as a starting point to study the possible packing of these chains. If we can have some luck in this direction, maybe one day we can also work on some very complex biological molecules like protein. So the last section is to search for the new materials with target properties. This is also a very attractive function, possibly, because all the systems I mentioned is to search for the lowest energy structures. So, but here, because the lowest energy is favored by nature, but for the material scientists, they don't view it in such a way. We are interested in materials due to the attractive properties. For instance, we want some super hard materials or superconducting materials. In this way, energy is not a good criterion. Instead, we should focus on properties. So we developed a formula, so-called hybrid optimization, to search for materials with target properties. So we split the searching into two levels. At the global level, we use the desired properties such as hardness, band gap, thermal conductivity as the criterion. While at the local level, we still use energy as the criterion to relax structures. So in this case, we are no longer exploring the energy landscape, but the landscape of the properties. We tried this function with a very simple example to search for, to optimize density, search for the densest crystal structures for carbon. As we know, carbon is diamond has the highest density among all the carbon molecules. However, in our search, we found that many structures can be denser than diamond. For instance, like all of these structures can find some analogs for between silicon oxides. And these structures are interesting not only because of the density, but also because of some other physical properties. For instance, they are mechanically also very hard. The hardness is comparable to that of diamond. and they have very fascinating optical properties. One is the dispersion, strong dispersion of light. All of these structures have stronger dispersions of light than that of diamond. As we know, diamond is shining because of the strong dispersion of light. So it means that if we can synthesize one of these structures, and this structure, this material will even outshine than diamond. So here I just to draw attention about this so-called new proposal which was recently issued by the White House. So Materials Genome Initiative. So President Obama has already initiated this proposal, and the aim is to help the business to discover, develop, and deploy new materials as fast as they can. So for this, it requires that computer modeling would play a much more important role in manufacturing industry. So I'd like just to list a possible future of this method of our crystal structure prediction can play a very important role in this project. So suppose if we study from an element, and study from a periodical table, and we pick some elements, and then we can use this method to search for the structures, crystal materials by energy or by physical properties, and then we can add with these materials available. We can further analyze the performances, and then we can decide if this material worth being synthesized. And if it doesn't satisfy this criteria, we can go back to the periodic table and pick another element. But all of this doesn't require any effort, doesn't require much cost in the laboratory or in the industry. But we can just purely design it purely on computer, and then we can further instruct if the material really has good properties. Then we can go to the lab and even factory to make these new materials. So it requires the concept of materials design, and I think our method can play a major role in this direction. So in summary, I introduced the basic concept of crystal structure prediction, the history, and the modern crystal structure prediction theory. And I illustrated this concept by three functions to discover the valuable stoichiometry compounds. Just remember I said that sodium chloride is no longer sodium chloride at high pressure, and we can also predict the molecular compounds and the molecular crystal from the molecular building blocks. And we can also optimize the properties so that it can provide a database for future material informatics. Finally, I'd like to thank many people, thanks our research group and our departments and the university, and also the funding support. Thank you.
This question about the method, what are the advantages of the genetic algorithm over other search algorithms that you can use? Yeah, it's a good question. First of all, I'd like to just point a minor limited version. So we don't call it like genetic algorithm, we call it evolutionary algorithm. So because like when we talk about the genetic algorithm, it involves this encoding. Yeah, but here in our research, we represent the crystal structure in real space. So we'd rather call it evolutionary approach. And
regarding the difference between evolutionary algorithm and other methods. So firstly, I'd like to there are two categories of methods which you can work for structural prediction. Firstly, first one is like long machine learning algorithms. So, for instance, people also, just like I mentioned, people can predict the structures from a huge database, and this is not. This is just, but this is not viewed as a artificial algorithm. So the difference is that they don't have this so-called self-learning process. And about the category of self-learning of the machine learning algorithms, which works for structural prediction, the advantage of this method is that they usually for other methods they can also perform this structure search, but they usually have to start with, they have a good starting point. For instance, if you predict a structure for carbon, you can use this method starting from graphite. Maybe you can finally find a diamond. But it means that it usually requires a good starting point. But for our method, we can basically just start from the most limited chemical information. You just need to specify, okay, just please perform a search with to find the most stable structures for carbon. Say like you create a box and then you put the carbon atoms in there, and then the method can automatically find the most comfortable configurations for this system. Yeah.
Just to follow up, how much mutation is necessary to make this work? I mean, obviously you have to have a parameter that controls the degree of mutation.
Yeah.
And too much mutation would cause it to bounce around.
Yeah, one should always find a balance between the genetics and the mutations. So I think it varies with different systems. For some systems, we especially require a large ratio of mutation, but for some systems, we don't need it. But I would like to say, if we work on some complex systems, mutation would be very essential for this point.
Thank you.
Is there a way of computing any defects or any?
You mean to predict some defects? We tried this, but when we talk about the defects, it's still at a very small, very micro scale. For instance, we can predict the defects with like hundreds of items, but if we want to represent the defects in the real materials, I think it's limited by the current computational power. Yeah. But I think in future we might be able to do this.
The long delay, you started off by talking about, I don't remember how long ago, but there was a famous paper written that said that there was a scandal that you couldn't solve this problem. And it took all this time since 1988 to solve the problem. Was that delay largely because of computational, you didn't have the computational capacity, or was it a limitation of theory or data? Or
both. I'd like to say both. Yeah. So at that time, obviously, we don't have a very good supercomputer, and also at that time, people are not aware about the advantages of the machine learning algorithms. They just use some ordinary method to predict crystal structures. But here we point out that using these artificial intelligence algorithms, we can benefit a lot from this. Of course, the computational power is another important factor. If we still stay if we go back to like 98.8, we use the same method. I'm not sure we can do many things. Yeah, with the computational power at that time.
Okay, thank you very much.
Thank you.